Okay. So hi everyone. So good afternoon all. Okay, so first of all let me know whether audio and video everything clear. So if it is not clear, please let me know in chat box, right? Okay, so I hope everything is clear here. I hope everything is clear, right? Okay, if it is not clear, please let me know here, right? Okay, so we are dealing with the subject electromagnetics. And here in electromagnetics we have started with time varying fields here. We have started with time varying fields. So in this we have started Faraday's law, right? So in the previous class we have started Faraday's law. Understood? Okay. So what we have seen here in Faraday's law, so whenever there is a change in magnetic flux, so that change in magnetic flux is going to induce what? Is going to induce an EMF around the closed loop. So that's what we have seen. Yes or no? Okay. Okay. Yeah. So we have given a mathematical expression to that Faraday's law, right? So previous class we have seen that we have taken a conducting loop like this, and here we have connected some galvanometer, right? Okay. So then we have moved the magnet, nearer to the loop and away from the loop. So whenever there exists a relative motion between the magnet and loop, we have seen that there will be a change in magnetic flux, and whenever there is a change in magnetic flux, we are seeing the deflection in the galvanometer. So that means whenever there is a change in magnetic flux, there induces an EMF around the closed loop, and that EMF is causing what? Is going to drive the induced current. Understood? Okay, so these things we have seen here in the previous class itself. We have seen all these things, right? Okay. Okay. So we have given the mathematical form to this Faraday's law. So what is the mathematical form of this Faraday's law here? That is nothing but whenever there is a change in magnetic flux, there induces an EMF around a closed loop. Understood? So here we have put some minus sign here. So this minus sign is because of what here? This minus sign is because of what? Is because of Lenz's law, right? Okay. Okay. So this is what we have seen here. And then we try to represent this induced EMF in terms of what? In terms of electric field. Yes or no? So we know how to represent the voltage around the closed loop in terms of what? In terms of electric field. So how we have represented here? So this is the induced EMF around the closed loop, that we can represent it as what here? Closed loop line integral E bar dot dl bar. So this represents what? This represents the circulation of electric field. Yes or no? So this is nothing but circulation of electric field around any closed loop. Circulation of electric field around any closed loop. Okay, so we can represent the EMF induced around any closed loop in terms of what? In terms of the circulation of electric field around any closed loop. Yes or no? Okay, so in electrostatics here, we have seen this one, right? So in electrostatics we have seen that the circulation of electric field around any closed loop is equal to what? Is equal to 0. Yes or no? So we call this one as what? As KVL, and here we called this electric field as what here? This electrostatic field is what? Is conservative field. Okay, so if the circulation of field around any closed path is equal to 0, then that vector field is said to be what? Conservative field. Yes or no? See, by applying Stokes theorem here, to this one, what you are going to get? I am writing directly here. You are going to get curl of E bar. Okay, so or otherwise I will write. Okay, so if I apply Stokes theorem to this one here, how I can write here? I can write this as a double integral curl of what? Curl of E bar dot what? Dot dA bar is equal to what? Is equal to 0. So that means this implies curl of E bar is equal to 0. Okay, so E bar is said to be what? E bar is said to be conservative field. So this is in case of what? This is in case of electrostatics here. right? Okay, so in electrostatics, the field, the electrostatic field is said to be what? Is said to be conservative field. Understood? Okay. Whereas time varying case, whenever you enter into time varying case, we have seen that this circulation of electric field around any closed loop is equal to what? Is equal to minus dou phi b by what? Dou phi b by dou t, minus dou phi b by dou t. So that means the circulation of electric field around any closed loop is not equal to what? Is not equal to 0. Is not equal to 0. Yes or no? It is equivalent to what? It is equivalent to minus of change in magnetic flux. Minus of change in magnetic flux. Understood? Okay. So that means here we cannot say, whenever we enter into time varying case, we cannot say this electric field as what? Now this electric field is not conservative. Now this electric field is not conservative. Yes or no? Okay. So when we can say the field is conservative here? Whenever the circulation of electric field around the closed loop is equal to 0 or curl of E bar is equal to 0, only in that case we can treat that field as what? Conservative field. Yes or no? Okay. So here we are clearly getting that the circulation of electric field around any closed loop is not equal to 0. It is equivalent to the change in magnetic flux. It is equivalent to change in magnetic flux, and hence here the electric field, is non-conservative. So here the electric field is what here? The electric field is non-conservative, right? Yes or no? That's what you have to understand here. So that's why whenever I am teaching that electrostatics part, I have specifically mentioned that electrostatic field. Okay, electrostatic field is conservative, but whenever we enter into time varying case, we should not say the electric field as what? We should not say electric field as conservative. So now it becomes what? Now it becomes non-conservative. It becomes non-conservative. Why it is non-conservative here? Because the circulation of electric field around any closed loop is not equal to 0 in this case. Okay. Next, we have seen that how to represent this magnetic flux. How to represent this magnetic flux? So how to represent this magnetic flux here? So we have already seen here mathematically how to represent this magnetic flux. So magnetic flux is nothing but the number of field lines that are penetrating through what? That are penetrating through the surface that is enclosed by the loop. Understood? Okay. So we have already seen this one. So phi b, we can represent it as what? Double integral b bar dot what? B bar dot dA bar. So that means this expression we can write it as what? Minus of dou by dou t into what? Double integral b bar dot what? B bar dot dA bar. So this is nothing but phi b. This is nothing but phi b. Understood? Okay. Okay. Yeah. So we got the integral form in this manner here. So that is the circulation of electric field around any closed loop is equal to what? Is equal to, so here integration is with respect to space and differentiation is with respect to time. So time operation and spatial operation both are independent to one another. So you can represent the same expression in this manner, that is a minus of double integral dou b bar by what? Dou b bar by dou t dot dA bar. So whether you represent in this manner or in this manner, it doesn't matter. It doesn't matter. Okay. So both are what? Both are same only, right? Okay. So what is the reason and all these things I have already explained here, right? Okay. Okay. So this we call as a integral form. Yes or no? This is what we call it as a integral form, or what? Integral form, or integral form. That's it. We call it as integral form of Faraday's law. Integral form of Faraday's law. Right? Okay. So now if you apply Stokes theorem here, if you apply Stokes theorem to this one, to LHS side, if you apply Stokes theorem, so then I can represent this as what here? Double integral curl of what? Curl of E bar dot what? Dot dA bar. So this is equivalent to what? Double integral here minus dou b bar by dou t dot what? Dot dA bar. Understood? Okay. So if you compare both, if you compare LHS with RHS, okay, so what you are going to get here? You are going to get curl of E bar is equal to what? Is equal to minus dou b bar by what? Dou b bar by dou t. Understood? Okay. So if you observe here, we are not getting curl of E bar is equal to what? We are not getting curl of E bar is equal to 0. We are getting curl of E bar is equal to minus dou b bar by dou t. Understood? So since curl of E bar is not equal to 0, so this electric field here, the electric field here is what? Is non-conservative. Is non-conservative. Understood? It is non-conservative, right? Okay, so these things you have to observe here. These things you have to observe. Okay, so this is the point form. This is the point form or a differential form, right? This is the point form or differential form of what? Of Faraday's law. Of Faraday's law. Understood? Okay. Okay. So these things we have seen in the previous session. Okay. 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 So next. Next, I have told that this minus sign here, this minus sign, that is V EMF is equal to minus of what? Minus of dou phi b by dou t. So I said that this minus sign is because of what? Is because of Lenz's law. Is because of Lenz's law, right? So I have explained what do you mean by Lenz's law. Understood? Okay. So you are going to have what? You are going to have, just I am briefly explaining here, you are going to have cause and effect, right? Okay. So what is the cause here? Cause will be change in what? Change in magnetic flux. So whenever there is a change in magnetic flux, the effect will be what? There will be an induced EMF. So this induced EMF is going to produce what? An induced current. So this induced current in turn is going to produce what? Induced magnetic field. Okay, so from Lenz's law we can say that always you are going to have cause and effect, and always this effect what? This effect opposes what? Opposes the cause. So that means here the effect is nothing but induced magnetic field and cause is nothing but change in magnetic flux. So this induced magnetic field will always opposes what here? Will always opposes change. Will always opposes change in magnetic flux. Change in magnetic flux. So we have seen that this change can be what? This change can be increase in magnetic flux, or it can be what? Or it can be a decrease in magnetic flux. Understood? Okay. So we have taken the loops here. We have taken a loop, right? Okay, we have taken a loop and we have moved the magnet. Let us say magnet is moving. Let us assume the magnet is moving towards the loop. So whenever the magnet is moving towards the loop, the number of field lines that are penetrating through the loop, are going to what? Are going to increase. So that means here in this case magnetic flux is what? Is increasing. So we have seen that whenever the magnetic flux is increasing here, so the induced magnetic field will try to oppose that increase. So we have seen that in this case, the direction of induced magnetic field will be exactly opposite to what here? Will be exactly opposite to actual magnetic field. So this is B actual. Understood? So whenever magnetic flux is increasing, we have seen that the induced magnetic field direction must be what? Must be exactly opposite to the actual magnetic field direction. Okay, so that means the induced magnetic field has to point in downward direction in this case. So in this case the current through the loop has to flow in which direction here? It has to flow in clockwise direction like this. Understood? Okay. So similarly whenever you consider the loop like this, and if the magnet is moving away from the loop, so in this case the number of field lines that are penetrating through the loop are going to what? Are going to decrease. So in this case magnetic flux is what? Is decreasing. Magnetic flux is decreasing. Right. So whenever the magnetic flux is decreasing, so what I have told here? The induced magnetic field direction will be along the direction of what? Actual magnetic field. So this is the actual magnetic field. Yes or no? This is the B actual. So B actual is pointing in upward direction. So here the induced magnetic field in this case will also point in which direction? In upward direction. Okay. So all this analysis we have done in the previous class itself. Right. Okay. Okay. So whenever flux is decreasing, the direction of B induced and the direction of B actual both must point in the same direction, and whenever the flux is increasing, in that case the direction of B actual and the direction of B induced must point opposite to one another. Understood? Okay. In terms of directions I am saying. Right. Okay. Okay. So all these things we have seen in the previous session itself. Right. Okay. Okay. So in this case, the induced magnetic field is trying to oppose the increase in magnetic flux, and here in this case, the induced magnetic field is trying to oppose the decrease in magnetic flux. Okay, always it tries to oppose the change in flux, right? Okay, okay. So we have done all this analysis in the previous class itself here. Just I am revising all those things. That's it, right? Okay. Okay. Now, one more thing I want to specify, that is, see here, generally, whenever we consider a loop like this, understood? Okay. So, I am mentioning that whenever it is flowing like this, I am calling this as what? I am calling this as anti-clockwise direction. And whenever I consider the loop, like this, okay, and if suppose this loop I am enclosing in this manner, let us say the current, let us assume the current is circulating in this manner. So this one I am considering it as what? This one I am considering it as clockwise. Understood? Okay. So next, what I have told here, so next we have considered the loop like this. If we consider the loop like this, understood? Okay. So I have told in the previous session that so if the current flows in this direction, if the current flows from lower to upper, so like this, understood? So I have told that consider this as what? Anti-clockwise direction, right? Okay. So next next, if we consider the loop like this, right? See, for the previous problems I am saying here, right? Okay. So in this case I have explained that, I have told that if the current is flowing in this manner, that means from up to down, so consider this as what? I have told that consider this as what? Consider this as clockwise direction. So I have told this already. Okay. So whenever I am explaining, I have told which one you have to choose anti-clockwise and which one you have to choose clockwise. So that's what I am mentioning every time, right? Okay. See here, in general here, this clockwise and anti-clockwise are just a conventions that we are following here. It is the convention that we are following. Okay. See here, if the person is watching this loop from top here, understood? So for him it appears to be anti-clockwise. So if the same person is looking at this loop from the bottom, then it appears as what? It appears as clockwise. Understood? So if you view this from top, it will appear as anti-clockwise. If you view the same thing from bottom, it appears as what? It appears as clockwise. Understood? So same is the case here. So if you view from top, it appears as what? It appears as clockwise. If you view from bottom, the same thing, it appears as what? Anti-clockwise. So here, if you view this loop from right side here, understood? Okay. So if you view this loop from right side, it appears to be what? It appears to be anti-clockwise. Right. Okay. So if you view the same loop from this side, it appears to be what? It appears to be clockwise. Understood? So if you view the same loop from this side, it appears to be clockwise. Whenever you view the same loop from this side, it appears to be anti-clockwise. So it all depends upon the reference here. What you are considering. Okay. So every time you cannot say take the reference top view, bottom view, or side view, here, left, right, like that. Okay. So whenever I am mentioning clockwise and anti-clockwise, I am saying that just follow this convention, right? So I am specifying the convention before considering it as clockwise or anti-clockwise. So that's what I am saying here. Whatever the convention you can follow here, you can follow any convention, it doesn't matter, right? Okay. Okay. So that's why what I am saying here is we are following this convention. So before I am saying anti-clockwise or clockwise, I will explain which direction you have to consider anti-clockwise, which direction we have to consider clockwise. So take it as a reference here. That's it. Understood? Just follow that one, right? Okay. 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 And similarly, if you consider the loop like this, right? Okay. So so you are saying this as what? You will say this as anti-clockwise. And if you consider the loop, like this, right? So this one I can say what? This one, I can say it as what? Clockwise. Understood? So how you are saying? You are looking this from out of the board, from out of the board. So from out of the board, if you look this, it is looking like anti-clockwise, it is looking like clockwise. So go behind the board here, go behind the board, okay, on the other side of the board, and if you look the same thing, it appears as clockwise and it appears as what? Anti-clockwise. Understood? Okay. So it all depends upon what is the reference you are considering and what is the convention you are following. You can follow any convention here, it doesn't matter. Understood? You can follow any convention, it doesn't matter. Right. Okay. Okay. Right. Next. Okay. We have seen we have seen different problems here based on Lenz's law. So with the help of Lenz's law, we can determine the exact direction of what? The exact direction of the flow of current. The flow of current. Understood? With the help of Lenz's law. Right? Okay. So now write down a problem here. Write down a problem. Right? So write down one problem here. Write down your problem. So two circular loops A and B have their planes parallel to each other, as shown in figure, Okay. So here they have given two circular loops like this, right? Okay. Right. So this is loop A and this is loop B. So loop A has a current moving in counterclockwise direction, as shown in figure, Okay. So in the figure they have given that the current is flowing like this, right? Anti-clockwise direction like this they have mentioned, right? Okay. Okay. So shown in figure. So A, if the current in loop A, decreases with time, then what is the direction of the induced induced current in loop B. What is the direction of the induced current in loop B? Will the two loops attract or repel? Will the two loops attract or repel each other? Okay, so B, repeat A if current in loop A increases with time. Okay. Okay, so this is the question they are asking here. What is the question? See here. Okay, see here what they are asking. So they have given two circular loops A and B. Two circular loops A and B have their planes parallel to each other as shown in figure. So this is loop A and this is loop B. So their planes are parallel to what? Are parallel to each other. Understood? Okay. So loop A has a current moving in a counterclockwise direction as shown in figure. So in loop A, the current is flowing in counterclockwise direction. That means this direction you have to consider as what? Counterclockwise or anti-clockwise. Understood? Okay. So the current is flowing in anti-clockwise direction or counterclockwise direction in this manner in loop A, right? Okay. Next, in A they have given that they are asking that if the current in loop A decreases with time, then what is the direction of the induced current in loop B? What is the direction of the induced current in loop B? Will the two loops attract or repel each other? Will the two loops attract or repel each other? See, what they have given here is they have given two loops whose planes are parallel to each other. So now they have given that in loop A, the current is moving in which direction? In anti-clockwise direction, and they have given that this current is varying with respect to time. So that means why it is varying with respect to time here? So they have told that this current in loop A is decreasing with respect to time. That means current is a function of what? Current is a function of time, and the value of the current is decreasing. The value of the current is decreasing with what? With time. The value of current is decreasing with time. Understood? Okay. So in that case, what they are asking here, what is the direction of the induced current in loop B? Will the two loops attract or repel each other? So this is what they are asking here. Okay. So here the current that is flowing in loop A is time varying current. It is time varying current. So the current is decreasing. With respect to what? With respect to time. It is flowing in anti-clockwise direction, and this current is decreasing with respect to time. Understood? See, we know that whenever the current is flowing in anti-clockwise direction here, so from right hand rule, we know that it is going to produce the B field in which direction? In upward direction. Yes or no? So whenever the current is flowing in anti-clockwise direction, we know that the B field it is going to produce in upward direction. So due to this loop here, in loop B there is no current now. There is no current now. Okay. So you are having only the current in loop A. Understood? So this current is going to produce what? Is going to produce the B field. In which direction? In upward direction. So that means the B field will be in which direction? The B field will point in upward direction. So this is the direction of the B field here, right? This is the direction of the B field, right? Okay. Okay. Now consider only loop B here. Consider only loop B. See here, this current is varying with respect to time. That means this current is decreasing with respect to time. So whenever this current is decreasing with respect to time, then what will happen here? What will happen? The number of field lines that are penetrating through this loop will also decreases with respect to time or not? Yes or no? So that means through loop B here, through loop B, the magnetic flux through loop B decreases with respect to what? With respect to time. Why it is decreasing here? Because this B field, whatever the B field it is producing, it is based on what? It is based on this current. Yes or no? Since this current is decreasing with respect to time, so the B field produced by that one will also decrease with respect to time. So the number of B field lines that are penetrating through this loop will gradually decreases with respect to time, since current is decreasing with respect to time. Understood? So that means the magnetic flux, what is the conclusion we can make? The magnetic flux through loop B is decreasing with respect to time. Okay, so we know that whenever the magnetic flux decreases with respect to time here, whenever the magnetic flux decreases with respect to time, then what will happen here? Tell me, what will happen? Whenever the magnetic flux decreases with respect to time, then what will happen? So there will be an induced magnetic field. So the induced magnetic field direction will be what? Will be exactly in the direction of what? In the direction of actual magnetic field. So whenever the magnetic flux is decreasing, what I have told here, the induced magnetic field direction must be what? Must be along the direction of what? Along the direction of actual magnetic field. Understood? So this is the direction of what? This is nothing but what? This is nothing but B actual. This is nothing but B actual. Okay, so B actual is pointing in upward direction. Since the flux is decreasing, so B induced will also point in which direction here? Will also point in upward direction. Will also point in upward direction. Understood? Okay, so if B induced is pointing in upward direction, means what must be the induced current around this loop here? What must be the induced current around this loop? So the induced current around this loop will flow in which direction? If the induced magnetic field is in upward direction, then the induced current will flow in which direction? Anti-clockwise direction. Okay, so that means in loop B, the current is going to flow. The current is going to flow in which direction here? In anti-clockwise direction, like this. Understood? Okay. Okay, yeah. So whenever the current, now if you observe here, the current is flowing in anti-clockwise direction. In loop A also the current is flowing in anti-clockwise direction. So we know that whenever the current is flowing in the same direction, then what they will do here? They are going to attract each other. Yes or no? We have already seen here while dealing with the Lorentz force equation, there we have seen that whenever you are having two current carrying wires carrying the current in the same direction, they are going to attract each other. So if the current carrying wires carrying the current in opposite directions, they are going to repel each other. Yes or no? Okay, so that's why here, since these two loops are carrying the currents in the same direction, so what they will do here? They are going to attract each other. Understood? Okay, so that means for A, what is the answer here? What is the answer? So then what is the direction of the induced current in loop B? So the direction of the induced current in loop B will be in what? Will be in anti-clockwise direction. So since in loop B the current direction and loop A the current direction, both are what? Both are same. They are going to what? They are going to attract each other. Okay. Okay, so in this case they are going to attract each other. Right? Okay. Okay, so next in B, what they are asking here? So they are saying that repeat A So that means you have to repeat A if current in loop A increases with time. So take the same problem. Now you have to analyze what happens if the current increases with respect to time. So we have analyzed what happens if the current decreases with respect to time. Now you have to analyze what happens if the current increases with respect to time. Okay, so that one you can easily do that here. See here. So here I am considering the two loops. So this is loop A, let us say this is loop B, right? Okay, okay. So loop A and loop B. So this is a loop A and this is a loop B. So they have given that the current in loop A is moving in which direction? In anti-clockwise direction, like this. Right, okay. So now here this current I is increasing with respect to what? Now you have to consider I is increasing with respect to time, understood? Okay, so now if you observe, still the current is flowing in which direction here? Anti-clockwise direction. So that means it is going to produce the B field. It is going to produce the B field in which direction? In upward direction only. Understood? Okay, so the magnetic field it is going to produce is in which direction here? It is going to produce the magnetic field in upward direction. Okay, so you can extend like this here. You can extend like this, no problem, right? Okay. So it is going to produce the magnetic field in upward direction. Now here, since the current is increasing with respect to time, so the magnetic field produced by this current will also increases with respect to time. So that means the number of field lines that are penetrating through this loop here, the number of field lines that are penetrating through this loop B will increases gradually, with respect to what? With respect to time. So that means here I can say the magnetic flux, is increasing. Yes or no? The magnetic flux is increasing with respect to what? The magnetic flux is increasing with respect to time. The magnetic flux is increasing with respect to time. Right? Okay. So we know that whenever the magnetic flux is increasing with respect to time, then what must be the direction of induced magnetic field here? So the direction of induced magnetic field must be exactly opposite to the direction of actual magnetic field. Okay. So these points or these observations are very, very important here. Right? Okay. Okay. So flux is increasing with respect to time. So here this is nothing but what? This is nothing but B actual. So B actual is pointing in which direction? Upward direction. So the induced magnetic field must point in which direction here? Here in this case the B induced must point in downward direction. Why here? Why? So whenever the flux is increasing, the direction of induced magnetic field must be what? Must be exactly opposite to what? Must be exactly opposite to what? Opposite to the direction of what? Direction of actual magnetic field. So that means here in this case induced magnetic field must point in downward direction. So if it is pointing in downward direction here, what must be the direction of induced current here? Now here the direction of induced current in loop B will be in which direction? Will be in clockwise direction. Understood? So that means here in loop B now the current is going to flow in clockwise direction. Now if you observe in loop A the current is flowing in anti-clockwise direction and in loop B the current is flowing in clockwise direction. So since the currents are flowing in opposite directions, so they are going to what? They are going to repel each other. Understood? Okay. So in this case loop A and loop B are going to what? Are going to repel each other. Why here? Because the current through loop A and the current through loop B both are what? Both are opposite to what? Both are opposite to one another. We know that whenever we are having two current carrying wires carrying the current in opposite directions, they are going to repel each other. Understood? Okay. Okay. Yeah. So that's why here the loops are carrying the currents in opposite directions and hence they are going to repel each other. Okay. Okay. Yeah. So this is a conceptual question based on what? Based on Lenz's law. Right? Okay. So I hope it is crystal clear here. Right? Okay. Right. Okay. So next, okay, see here. Okay. Now see here. I have told that in electrostatics we know that electric field is what? Electrostatic field is a conservative field, and we have seen that the work done in a conservative field is independent of what? Is independent of the path you are choosing. Yes or no? I have told this point or not? So in a conservative field, the work done is independent of what? Is independent of the path you are choosing. But here in Faraday's law, the circulation of electric field around any closed path is not equal to 0. It is equivalent to what? It is equivalent to change in magnetic flux. So that means here, E field is called as what? Non-conservative field. So non-conservative field means what here? It has to depend upon what? The work done will be depend upon what? Will depend upon the path you are choosing. It depends upon the path you are choosing. Understood? Okay. So whereas in electrostatic case, electric field is a conservative field, and in a conservative field the work done is independent of the path, whereas here in Faraday's law the circulation of electric field around any closed path is not equal to 0. So that means here the electric field is non-conservative. So whenever we enter into time varying case, here the electric field is what? Is non-conservative. Understood? Okay. So in a non-conservative field, the work done will depend upon what? Will depend upon the path, right? Okay. So keep these points in mind here. Keep these points in mind, right? Okay. So now I will give you one simple question for you here. I will give you simple question for you. See, we can frame many very good conceptual questions based on Faraday's law here. Okay. So see here. So I am giving this circuit here. Let us say this is R1, let us say this is R1, okay. So here let us say this is 1 volt, and here let us say this is R2, right? Okay, okay. So let us say R1 is equal to 1 ohm and R2 is equal to 9 ohm, right? Okay. So now here I am considering this node or this point as A, and this point and this point as B, right? So this point I am considering as A and this point I am considering as B, right? Okay. Okay. So now here now here we know that the current in the loop is going to flow in this direction. We know this, right? Okay. Okay. So now if I ask you so we know that the current is going to flow in this direction. We know that, right? Okay. Now here if I ask you, now in this circuit here, you can apply what here? You can apply what? You can apply KVL, right? You can apply KVL, because here we are dealing with what? We are dealing with the DC source. Yes or no? Okay. Okay. So nothing is going to vary with respect to time in this circuit, right? Okay. So here you can happily apply what here? For this circuit you can happily apply KVL, right? Okay. So now, so you are applying KVL means what here? You are applying KVL means the circulation of electric field, around this closed path, will be equal to what? Will be equal to 0. Will be equal to 0. Yes or no? See, that means see here the current is flowing like this, right? So the current is flowing like this. So here the current is flowing like this, here the current is flowing like this, right? Okay. So let us say this is I, current is I, right? Okay. So the current will flow from higher potential to lower potential. So that means here I can put plus and here minus, and here I can put here plus and here minus, and the battery, for battery here it will be plus and here it will be what? Minus. Understood? So that means here, So here this is nothing but what? This is nothing but if I consider this as a perfect conductor here, this as a perfect conductor. So inside the perfect conductor, so electric field inside a perfect conductor will be equal to what? Will be equal to 0. Okay, so remember that point here. Now see here. So now here here it is plus and here it is minus. So that means here the electric field is pointing in downward direction. So this is electric field, right? Okay. So now this is electric field, right? Now what I am doing here is I am trying to determine this circulation of electric field here. The circulation of electric field around any closed path is equal to what? Is equal to 0. Yes or no? So what do you mean by circulation of electric field around this closed path? That's what I am explaining. Okay. So here the electric field is pointing in this direction. Now let us assume you are moving around the loop here, in clockwise direction like this. Let us assume you are moving around the loop in clockwise direction like this. Understood? Okay. So you started from A. Okay, you started from A. So from this point to this point here, you are having what? You are having a perfect conductor. So over this region, if you do integral E bar dot dl bar here, what you are going to get? You are going to get 0, because inside a perfect conductor, electric field will be equal to what? Electric field will be equal to 0. So that means if you do integral E bar dot dl bar over this section, you are going to get 0. So next I am doing integral E bar dot dl bar over this section here. I am doing integral over this section. I am doing integral E bar dot what? E bar dot dl bar. Now here E bar is pointing in which direction? Electric field is pointing in downward direction, and dl bar, that means the loop direction. The loop direction is also pointing in downward direction. I am moving around the loop like this. Understood? Okay. So integral E bar dot dl bar is pointing in which direction here? Okay, electric field is pointing in downward direction and dl bar is also pointing in downward direction. So E bar dot dl bar, you will get what? You will get some positive value here. Right? Okay. Next, from here to here, if you do E bar dot dl bar here, E bar dot dl bar, what you are going to get? You are going to get 0, because inside the conductor the electric field will be what? Electric field will be equal to 0. Perfect conductor I am considering. Okay. Now if you consider battery here, okay, so you are moving in upward direction, but here if you observe the battery, here plus and here it is minus. So that means here the electric field is pointing in downward direction here. Understood? Electric field is pointing in downward direction, but you are moving in upward direction. Understood? So that means here what you are going to get? You are going to get E bar dot dl bar. You are going to get E bar dot dl bar. Here you are going to get what? You are going to get negative value. Why here? Here E bar is pointing in downward direction and the loop is pointing in upward direction. So you are going to get integral E bar dot dl bar as what? As negative. Understood? Okay. So next, from here to here, the electric field is pointing in this direction, and dl bar is also pointing in upward direction. So in this case, if you do integral E bar dot dl bar, so this value will be what? This value will be positive. Understood? Okay. Okay. So now now see here, from A to B here, from A to B, what is the potential here? So VAB, I can write VAB is equal to what? Is equal to integral A to B E bar dot what? E bar dot dl bar. Right? Yes or no? Okay. See, from A to B, if you move from A to B, what you are going to get? VAB is equal to what? Integral A to B E bar dot what? E bar dot dl bar. Right? Okay. Okay. Next. Okay. Okay. So let us consider this point here. Let us consider this point. So this point as C. Let us consider this point as C. Okay. So from B to C here, from B to C, from B to C, right? Okay. So integral E bar dot dl bar will be what? Will be negative. Will be negative. So this is nothing but what? This is nothing but battery potential, right? Okay. So this is nothing but battery potential. I am writing this battery potential as a minus V battery. Minus V battery. Why here? Because it is negative. Integral E bar dot dl will be negative. So which is nothing but what? Which is nothing but battery potential. So I am writing it as what? Minus V battery. Next, from C to A. From C to A. Okay. So from C to A, from C to A. So from C to A, what you are going to get here? You are going to get integral C to A E bar dot what? E bar dot dl bar. E bar dot dl bar. Right? Okay. So this potential I am naming it as from here to here. Here to here, you are having the potential drop across R1. So I am naming this as VR1, right? So this one I am naming it as VR2, VR2. Okay. So now if you what is the circulation of electric field around this closed path here? Circulation of electric field around this closed path is nothing but what? Integral A to B plus what? Plus B to C plus what? C to A plus C to A. Understood? So that means you have to add up all this. You have to add up all this. So that means what you are going to get? VR2 minus what? Minus V battery, right? Okay. So plus VR1. So the circulation of electric field around this closed loop is equal to what? Is equal to 0. Is equal to what? Is equal to 0. So this we call it, this we are calling it as what? This we are calling it as KVL. Right? Okay. So here what is V battery here? V battery is equal to what? V battery potential is equal to what? Is equal to VR1 plus what? VR1 plus VR2. Understood? So this is nothing but what? This is nothing but KVL here, right? Okay. So just I have explained how we are getting this potential, how we have to calculate how we are calculating the potential in terms of what? In terms of electric field. Understood? Okay. Okay. So this is how you have to calculate the circulation of electric field around the closed loop. Around the closed loop. Understood? Okay. Okay. So if you add up all this here, if you add up all this around this closed path, that is equivalent to 0, which we are calling it as what? Which we are calling it as KVL. Which we are calling it as KVL. Understood? Okay. Okay. So now see here. Now see here. So I have considered this is R1, right? Okay. Just I tried to show you how to what do you mean by this circulation of electric field around this closed path. Okay. So this is nothing but what? This is equivalent to 0. So this we call it as what? This we call it as KVL, right? Okay. Okay. So here R1 I have considered, right? Next, battery. So this is the battery. Next, here this is R2. So here R1 is equal to 1 ohm, R2 is equal to what? R2 is equal to 9 ohm, and here let us assume this potential is 1 volt. Let us assume this potential is 1 volt, right? Okay. Okay. So this is A and this is what? This is B. And this is A, this is B, right? Okay. Okay. So now if you move from A to B, right? Okay, if you move from A to B in clockwise direction like this. So from here to here you have moved in this direction, that is in clockwise direction, let us assume. Okay. So now what is VAB here? What you are going to get? VAB whenever you are moving in clockwise direction, See, I have told that the work done around any closed path is independent of what? Is independent of the path. Is independent of the path. If whenever you are dealing with what? Whenever you are dealing with the conservative field. So here the electric field is what? Here the electric field in this circuit is what? Is a static field. So that means the work done around this closed path. The work done from one point to another point will be independent of what? Will be independent of the path you are choosing. See, VAB is equivalent to what? VAB is nothing but what? Is nothing but integral a to b e bar dot what? E bar dot dl bar. See, we know that e bar is nothing but what? E bar, I can write it as what? F bar by what? F bar by q. E bar is nothing but F bar by q. Okay, so this one I can write it as integral a to b 1 by q f bar dot dl bar. So f bar dot dl bar will represent what? Work done. Yes or no? F bar dot dl bar from a to b will represent what? Will represent work done. So work done per unit charge. Work done per unit charge in moving from a to b. So that is nothing but what? That is nothing but the potential. The potential from a to b. From a to b. Potential difference from a to b. Understood? Okay. Yeah. So now see here. So what we are going to get here? See, if we deal network theory in terms of EMT, it is going to be very tough. Yes or no? Okay. See here. So here, what is the current that is flowing in this circuit here? I is equal to what? I is equal to, so what is the voltage? Total voltage is nothing but 1 volt divided by what? Divided by R1 plus R2. So that is 1 plus 9 ohm. So 1 volt divided by 1 plus 9 ohm. So that is how much here? 0.1 amperes. It is flowing in which direction? Clockwise direction. It is flowing in clockwise direction. Okay. So that means here the current I is equal to what here? Is equal to 0.1 ampere. Current I is equal to 0.1 ampere. Right. Okay. Yeah. So now here, what is the potential difference between A and B here? What you are going to get? So VAB is equal to what? Is equal to drop across this resistor or not? Yes or no? So what is the drop across this resistor here? 0.1 into 9 ohms. So that is how much here? You are going to get 0.9 volts. You are getting 0.9 volts. Right. Okay. So now see here. If suppose you move from A to B in anti-clockwise direction like this here. If you move from A to B in anti-clockwise direction like this. Okay, so then what is VAB you are going to get? Tell me, what is VAB you are going to get? If you move in anti-clockwise direction, then what you are going to get? See here, the current is flowing like this, it is flowing like this. So here the current is going to flow like this. Understood? Okay, so that means here it is plus and here it is nothing but what? Minus. So now what is VAB here? What is the potential drop from A to B? What is the potential from A to B? Tell me here. So here you are having 1 volt and here what is the drop here? R1 is equal to 1 ohm and I is equal to what? I is equal to 0.1 ampere. I is equal to 0.1 ampere. So 0.1 into 1, that means 0.1 volts. So here the drop is 0.1 volts and here it is nothing but what? 1 volt. So what is the total potential difference from A to B? VAB is equal to what? 1 volt minus what? Minus 0.1 volt. So that is how much here? That is also equal to what? 0.9 volts. That is also equal to 0.9 volts. Yes or no here? Okay. So whether you move from A to B in clockwise direction or you move from A to B in anti-clockwise direction, you are going to get what? You are getting the same value. Yes or no? So if you move from A to B, you are getting what? You are getting 0.9 volts, or if you move in A to B in anti-clockwise direction, so then also what? Then also you are getting what? VAB is equal to what? Same value, that is 0.9 volts. So the work done per unit charge in moving from A to B in clockwise direction will be same as what? Will be same as the work done in moving the unit charge from A to B in anti-clockwise direction. So that means what I mean to say here is the work done in a conservative field is independent of what? Is independent of the path. It is independent of the path you are choosing. So that's why whether you move in clockwise direction or anti-clockwise direction, you are getting or ending up with the same result. Yes or no? Okay, so that's what I want to mention here, right? Okay, now see here. Now see here. So I am considering the, now what I am doing here is I am removing this 1 volt source here. I am removing this 1 volt source. I am removing this 1 volt source, right? Okay. So then the circuit will become what here? So then the circuit will looks in this manner. So here let us say this is R1. Okay. So there is no potential here. There is no potential, right? Okay. So I have removed the battery. There is no battery, right? Okay. So now here I am just simply considering the loop like this. So here you are having R2. This is R2. Okay. So R2 is 9 ohms. R2 I am considering it as 9 ohms, and R1 I am considering as what? 1 ohm. 1 ohm. So now let us assume in this case, let us assume okay. So okay, so let us assume here the B field, is pointing, into the board here. Let us assume B field is pointing into the board. Right. So let us assume B field is pointing into the board. And this B field is a function of what? Is a function of time. Let us assume B field is a function of time, and so I will give some function here. Okay. So B of t is equal to what? B of t is equal to, let us consider t into minus az cap, right? So B field is varying as what here? B field is varying as what? Is varying as a t, and it is pointing in which direction? Negative z direction. So let us consider this as x-axis, right? And let us consider this as what? Let us consider this as y-axis. So here I have given the B field here. B of t is equal to what? Is equal to t into minus az cap. That means here the B field is varying with respect to what? Varying with respect to time, and it is pointing in which direction? Negative z direction. Understood? Okay. So with respect to time, how whether it is increasing or decreasing with respect to time. See, as t increases, B field is also going to increase. It is just like a ramp function or not? Okay. So generally in practice we don't have this type of fields here. So just for mathematical purpose I am taking this, right? Okay. Yeah. So as t goes on increases, what will happen here? B field will also increases with respect to time, and it is pointing in which direction? It is pointing in negative z direction. Okay, so this is the B field, right? Okay. Yeah. Okay, so now let us consider this area of the loop here. Let us consider area of the loop. I am representing this as A bar is equal to what? A bar is equal to 10 az cap meter square. Okay, so the area of this loop here, I have given as what here? I have given as a 10 az cap meter square. So that means what is the direction of this surface area? You have to choose. So it is pointing in what? It is pointing in az cap direction. See, the direction of any surface is given by what? Is given by unit normal drawn to that surface. So you can draw the unit normal either in outward direction, or you can draw the unit normal into the board. Understood? But here they have specifically mentioned that consider the area of the loop as a 10 meter square, and the direction of area is representing in which direction? It is pointing in az cap direction. That means it is pointing in out of the board. Understood? Okay, so this is what they have given here. So they have given B field, and they have given what? They have given area of the loop. Understood? Okay. Yeah. Okay. So now okay, so now here let us consider this point as A, and let us consider this point as B. Let us consider this point as A and this point as B, right? Okay. So now here what I am doing here is I am connecting to this end here. At this end I am connecting an voltmeter. I am connecting an voltmeter. So let us say that is V1, right? So this is not voltage source here. This is nothing but what? This is nothing but voltmeter. Voltmeter. I have connected a voltmeter. Okay. So what is the purpose of voltmeter here? So the purpose of voltmeter is to measure what? Is to measure the potential difference across this terminal, across these terminals. Understood? Okay. Okay. Yeah. So next, on the other side, on this side also, I have connected. Okay. I will. Right. So on the other end also, so on this side I am connecting another voltmeter. Let us say this is V2. Okay, so this is nothing but what? This is nothing but voltmeter here. This is not voltage source, this is voltmeter, remember that. Okay, so this is voltmeter and this is also voltmeter, right? Okay, so what these voltmeters will do here, it is going to measure the potential drop across these terminals, and it is going to measure the potential drop across these terminals. Understood? Okay, okay, yeah. Okay, so now here okay, right. So now here we try to determine, we know that whenever there is a change in magnetic flux here, we know that there induces what? There induces an EMF, around the closed loop. Right. Okay. So here what is happening here? Here you are having the B field. So this is nothing but B field, right? Okay. So this is nothing but B field, right? So this B field is pointing into the board and it is varying with respect to time as what? T. So that means with respect to time, if you draw the graph here, let us say this is T and this is B of T. So it is varying with respect to time linearly, like this. Yes or no? Okay. So that means with respect to time, the B field is increasing and it is pointing into the board. So B field is increasing with respect to time and it is pointing into the board. So that means what will happen here? The flux through this surface here, is going to increase or not? Yes or no here? See, the B field is pointing into the board. The number of B field lines that are penetrating through this loop is called as what? Is called as magnetic flux. Understood? So since the B field is increasing with respect to time, so that means the number of field lines that are penetrating through this loop are increasing with respect to time. So if the flux is increasing with respect to time, okay, if the flux is increasing with respect to time, then we know that what here? We know that whenever there is a change in magnetic flux, okay, so what will happen here? There induces an EMF and that EMF is going to induce what? Is going to induce the current. So in order to determine the direction of current, you have to determine the direction of what? Induced magnetic field. So what must be the direction of induced magnetic field here? Here. See, since the flux is increasing into the board, okay, so the induced magnetic field has to oppose what? Has to oppose this increase. So I have already told that whenever flux is increasing, the induced magnetic field direction will be what? Will be exactly opposite to what? Exactly opposite to actual magnetic field direction. Now here the actual magnetic field direction is pointing into the board. So that means the induced magnetic field direction must point in which direction here? Out of the board. Okay. So first you have to identify that B induced will point in which direction? Will point in plus AZ cap direction, okay. So if B induced is pointing in out of the board here, I am representing B induced, this is B induced, right? Okay, so if B induced is pointing in is pointing out of the board, if B induced is pointing out of the board, then what is the direction of the current here? What is the direction of the induced current? So the direction of the induced current in this case, it is going to flow in which direction? In anti-clockwise direction. It is going to flow in anti-clockwise direction. Okay, so that means here you are going to have induced current here. You are going to have induced current. Okay, so induced current is going to flow in which direction? In anti-clockwise direction, like this, right? So this is the induced current. This is the induced current, right? Okay, so the induced current is flowing in this direction. So that means what is the induced EMF here? What is the induced EMF? See, we know that from Faraday's law, the induced EMF is equal to what? Is equal to minus dou phi b by what? Dou phi b by dou t. Dou phi b by dou t. So we try to determine the induced EMF. So what you are going to get? Tell me what you are going to get. So this is equal to, so minus dou by dou t. So where phi b is nothing but what here? Phi b is nothing but what? Phi b is nothing but B bar dot what? B bar. I can write B bar dot A bar directly here. I can write B bar dot A bar directly. Why? Means here the B field is independent of what? B field is independent of space. Yes or no? See, generally phi b is equal to what? Is equal to double integral B bar dot what? B bar dot dA bar. Right. So here B field is a function of time, but it is independent of what? But it is independent of space. Understood? So if it is independent of space, then it becomes constant with respect to what? With respect to this spatial operation. So you can take a B field outside the integration. So then B bar dot double integral dA bar is equal to what? Is equal to B bar dot what? B bar dot A bar. So in this manner I can directly represent phi b here, that is B bar dot A bar. Right. Okay. So now what is this B bar dot A bar here? So B bar is nothing but what? T into what? T into minus AZ cap. T into minus AZ cap. Right. Okay. T into minus AZ cap dot what? Dot A bar. A bar I have given as 10 AZ cap. 10 AZ cap. Right. 10 AZ cap. So this is nothing but phi b. This is nothing but B bar dot A bar. That is nothing but phi b. Understood? Okay. So if you do this, what you are going to get? So minus dou by dou t, minus dou by dou t into what? Into, so t into minus AZ cap dot 10 into AZ cap, you are going to get minus 10t, minus 10t. So if you differentiate this, what you are going to get here? Here minus will get cancelled. So then you are going to get what? You are going to get simply 10 volts, right? So you are going to get 10 volts. So this is the induced EMF value. This is the induced EMF value, right? So the induced EMF around this closed loop here, the induced EMF around this closed loop is how much here? Is 10 volts. See, remember that we have not connected any battery in this circuit here. We have not connected any battery in this circuit. We have just connected voltmeter at this end and another voltmeter at this end. Okay, it is just to measure what? It is just to measure the potential difference between A and B. Understood? Okay. Okay. Now see here. So VEMF is equal to 10 volts. So therefore I induced is equal to what here? Therefore I induced. So the current that is induced in the loop is equal to what? Is equal to VEMF divided by what? Divided by R1 plus what? R1 plus R2. Ohm's law is valid here. Ohm's law is valid, right? Okay. Ohm's law is valid, but KVL is not valid. Yes or no? See, VEMF is nothing but what? VEMF is nothing but what? Is nothing but the circulation of electric field around any closed loop. Yes or no? This is not equal to 0. This is equivalent to what? Change in magnetic flux. Understood? So you should not apply KVL here. KVL is not valid here. Understood? So you are applying what? You are applying Faraday's law, right? Okay, so remember that. And here this electric field here is what? Non-conservative field. This electric field here is non-conservative field. Okay, so remember all these things here. So Ohm's law is valid. V equal to IR is valid. Understood? Okay. Okay. So I induced is equal to V EMF by R1 plus R2. So where V EMF is equal to how much here? 10 volts divided by R1 plus R2. So that is one value I have taken as 1 ohm and another one as 9 ohm. So 1 plus 9, you will get what? You will get 10 ohm, right? So 10 volts and here 10 ohm. So you are going to get what? You are going to get 1 ampere. You are going to get 1 ampere. Okay? Okay, yeah. So now see here. Now see here. Now see here. So this induced current, we got it as what here? We got it as 1 ampere. So we got it as 1 ampere. This is 1 ampere. So this is 1 ampere, right? Okay. Okay, yeah. So now, so the current is flowing like this. So here I can put here plus and here it is minus, right? Okay. Okay, yeah. Now tell me what is V2 here? What is V2? Tell me what is V2? See, V2 is nothing but what? V2 is going to measure the potential difference between what? A and B. The potential difference between A and B. So V2 is going to measure the potential difference between what? Between A and B. Understood? Okay. So what is the potential difference between A and B? What you are going to get? Tell me what you are going to get. Tell me here. So I am copying this diagram here. Okay. So here this V2 will measure the potential difference between what? Between A and B. Understood? Okay. So V2 is nothing but what? Is nothing but the potential difference between A and B. Right? Okay. Okay. Yeah. So now see here. Okay, see here the current is flowing. The current is flowing from where to where? The current is flowing from here to here. Yes or no? In upward direction. The current is flowing from here to here in upward direction. So that means this current I induced is equal to what here? Is equal to, we know that the current will always flow from higher potential to what? Lower potential. So this I induced, I can write it as what here? I can write it as I induced is nothing but what? VB minus VA divided by what? Divided by R2. So I can write I induced as VB minus VA divided by what? Divided by R2. Understood? Okay. Okay, yeah. So from here VB minus VA is equal to what? Is equal to I induced into what? I induced into R2. I induced into R2. Okay. So I induced is how much here? I induced is how much? I induced we have calculated. Yes or no? It is 1 ampere and R2 is how much here? R2 is nothing but 9 ohm, right? Right? Yes or no here? I induced and R2 is 9 ohm. So what you are going to get? You are going to get here 9 volts. So this is nothing but what? VB minus VA. So but V2 is nothing but what? V2 is going to measure the potential difference between what? Between A and B. So that means it is going to measure VA minus what? It is going to measure VA minus VB. Understood? That is the reading of V2. Okay. So therefore V2 here, V2 is equal to what? V2 is equal to minus of what? Minus of VB minus VA. Yes or no? Okay. So you can say, or you can write directly here, right? So V2 is equal to what? V2 is equal to VAB. V2 is equal to VAB. So VAB is equal to what here? VAB is equal to, so this is nothing but what? This is nothing but VBA, right? So V2 is equal to VAB. So I can write VAB, which is equal to what? Which is equal to VA minus what? VA minus VB. So that is equal to what? That is equal to VB minus VA is 9 volts. So VA minus VB will be how much here? Will be, you will get minus 9 volts. You will get minus 9 volts, right? So that means therefore V2 is equal to VAB, which is equal to what? Which is equal to minus 9 volts, right? Okay. Okay. So here V2 will measure the potential difference between A and B. Potential difference between A and B as you move from what? As you move from A to B. As you move from A to B, right? Okay. So as you move from A to B, right? So you are going to get what? VA minus VB. So we have calculated VA minus VB as what? VAB, that is equal to what? That is equal to minus 9 volts. So that is at this end here. So this is, we have moved in clockwise direction. Next we are moving from A to B. We are moving from A to B in which direction here now? We are moving in anti-clockwise direction. We are moving now in anti-clockwise direction. So now what will happen? We will see. Okay. So now here also I can write this V1. This V1 will measure what here? Will measure the potential difference between what? A and B. It is going to measure the potential difference between A and B. So that means V1 here is equal to what? Is equal to VAB. But here it is in which direction here? Here you are moving in which direction? In anti-clockwise direction. So you are moving in anti-clockwise direction. Understood? Okay. So now see here. Now here VAB, what you are going to get here? Tell me. In this case, VAB is equal to what? Tell me what you are going to get. See here, here I induced is flowing in this direction, and here this is R1. So I induced here, I induced in this case. So we are dealing with anti-clockwise direction here. Now you are moving with anti-clockwise direction, right? Okay. So now this I induced is equal to what? So this I induced is equal to what? So the current is flowing from A to B. The current is flowing from A to B. So that means VA minus what? VA minus VB divided by what? Divided by R1. So from here, what you are going to get here? What you are going to get? VA minus VB is nothing but VAB, which is equal to what? Which is equal to I induced into what? I induced into R1. I induced into R1. Right? Okay. So I induced into R1. So here I am moving in anti-clockwise direction, and here I have moved in which direction here? Here I have moved in clockwise direction. So this is the analysis for moving in clockwise direction, right? Okay. Okay. So now here what you are going to get? VAB. So here this VAB is nothing but what? Is nothing but the reading of the voltmeter V1. So that is V1 is equal to VAB is equal to what? Is equal to I induced. I induced is 1 ampere, and R1 is how much here? R1 is 1 ohm. R1 is 1 ohm, right? Okay. So that means here this voltmeter is going to read how much here? It is going to read 1 volt. It is going to read 1 volt, right? Okay. Okay. So if you observe here, whenever you are moving in clockwise direction, so this V2 is going to measure from A to B in clockwise direction. Understood? So we have calculated this A to B. We have calculated this potential difference from A to B as you move from A to B in clockwise direction. So in this case, we got V2 as what here? The reading of voltmeter. We got it as what? We got it as minus 9 volts. We got it as minus 9 volts. Right? Okay. So whereas here, if you move from A to B, in anti-clockwise direction here. If you move from A to B in anti-clockwise direction, so here what we got here, what we got, the potential or the reading of this voltmeter or the potential difference between A and B, what you got it as what, 1 volt. Yes or no? Okay, so that means what here, so the here the work done from VAB is nothing but what, here this V2 VAB, this means what, this is the work done in moving the unit charge from A to B in clockwise direction. So we are getting it as minus 9 volts. So here as you move in anti-clockwise direction, so the work done in moving the unit charge from A to B in anti-clockwise direction. So for this one we got it as what here, we got it as 1 volt. So that means here the work done is depending upon what, is depending upon the path. Why here? Because now you are dealing with what, you are dealing with non-conservative field, yes or no? Okay, yes or no here? So here the EMF induced, here we have not connected any batteries in the circuit here, okay, but still how the current is flowing here, because of change in magnetic flux. So whenever there is a change in magnetic flux, we know that there will be an induced EMF, and because of that induced EMF you are going to see an induced current. Understood? Okay. Okay, here. So here in this circuit you don't have any voltage sources. So here we try to measure the potential difference between A and B as you move in clockwise direction. We got it as what here, minus 9 volts. As you move in anti-clockwise direction, we are getting it as what, 1 volt. So that means the work done in moving an unit charge from A to B in clockwise direction will be different, and A to B in anti-clockwise direction will be what, will be different. So in this case the work done is depending upon what, is depending upon the path. Why means here the electric field is what here, non-conservative field. Yes or no? Here the electric field is non-conservative field, right? Okay, so whereas in this case here, in this problem, whether you move in clockwise direction, here we have connected a battery, so in this case whether you move in clockwise direction or you move in anti-clockwise direction, what you are getting here, VAB is equal to what, 0.9 volts, and VAB here if you move in anti-clockwise direction also you are getting what, you are getting the same voltage. Why? Here the electric field is what, is conservative. Here the electric field is conservative. So here we have applied this one here, that is the circulation of electric field around this closed loop is equal to 0 is valid here, Yes or no? That means KVL is valid here. Understood? So that's why we are getting what, we are getting the same value whether you move in clockwise or anti-clockwise, it doesn't matter, because here this is nothing but what, this is nothing but a conservative field. Here the electric field is a conservative field. Understood? Okay. Whereas here we are dealing with what, we are dealing with non-conservative field. So in case of non-conservative field, the work done is going to depend upon what, is going to depend upon path you are choosing. So that's why we are getting what, that's why we are getting the readings as what, readings as different, right? Okay. So here if you move in clockwise direction you are getting minus 9 volts, if you move in anti-clockwise direction you are getting 1 volt, right? Okay. So it is somewhat hard to digest here, because this is the first time maybe we are dealing with the non-conservative field. Okay, but you have to understand this concept here, right? Okay. Okay. So okay, please go through this one here, please go through this one once, okay, and try to understand each and every step whatever I have done, right? Okay. Okay. So please try to practice here, please try to practice on your own. So this one and this one, So then you will get a crystal clarity, right? Okay. Okay. So with this I am winding up the session for today. With this I am winding up the session for today. So tomorrow exactly at 4 p.m. Tomorrow exactly at 4 p.m. we will meet here, right? Okay. So stay safe and keep learning. Right? Okay, so tomorrow we will meet exactly at 4 p.m. So stay safe and keep learning. So until then, okay. So until then, take care. Bye bye.